Today's lesson 6 is all about solving rational equations and inequalities. A rational equation is any equation that contains one or more rational expressions. We're going to use two different methods. The preferred method is to eliminate the fractions by multiplying each side by the least common denominator. And I'm not going to read through the procedure, but we'll just jump into the lesson and model the procedure as we go along. For example 1, we want to solve and check our solutions, and looking at the two denominators, 5 and 4, we know that 20 would be our least common multiple, so we would use 20 as the multiplier on both the left and the right to eliminate the fraction and have just a linear equation to solve. So 20 is our magic number in this case. We want to multiply both sides by 20. In our first example, 5 divides 20 4 times, so we're multiplying 4 times x minus 2. And then in the second term, 4 divides 20. In this case, 4 divides 20 5 times. So our second term is multiplying minus 5 times x minus 5, and then 20 times negative 2 is negative 40. Using the distributive property, 4x minus 8 minus 5x plus 25 equals negative 40. So 25 minus 8 is 17, and 4 minus 5 is negative 1. And if we move the x to the other side and the 40 to the left side, we have x is equal to 57. To save time, I'm not going to substitute back in. We don't want the video to run really long. In this next example, you notice that both of the denominators are the same. So in this particular example, if the denominators are the same, then all we need to do is care about the numerators, so we can solve for the equation that results from our numerators. X minus 1 is equal to x squared plus 2x minus 3. Collecting all the terms on one side, we have x squared plus x minus 2 is 0, so x plus 2 times x minus 1 would be 0, and using the zero product property, x plus 2 is equal to 0 when x is negative 2, and x minus 1 is equal to 0 when x is equal to 1. Now, checking back in the original problem, you noticed our denominator was x plus 2. So negative 2 would be extraneous, and we wouldn't be allowed to have x equals negative 2. That would be considered an extraneous solution. In example 2, you notice we have one variable x and another that has x in the denominator. So if we multiply both sides by x, we can clear out the fraction in this second fraction of 12 divided by x. But whatever you do to the left, you need to do the same to the right. So we have x squared, and then this x divides away this x. So that's x squared minus 12 equals 1x. And x squared minus x minus 12 is equal to 0. Then we're going to factor and set each factor equal to 0. When is x minus 4 0? When x is 4. And when is x plus 3 0? When x is negative 3. And again, it's important to note that we had here x can't be 0. In either case, we did not have that situation. Oop. But I've marked off negative. It cannot be, but I do mean x is negative 3, not is not. Part B is the same way. If we multiply through by x on each term, x here, and x here, we'll clear that fraction. So x squared plus 6 equals 5x, when x squared minus 5x plus 6 equals 0. And the factors are x minus 3 and x minus 2. And x minus 3 is 0 when x is 3. X minus 2 is 0 when x equals 2. And looking back at the original, our restrictions would again be at 0. In example 3, we got a little more going on. You can see that x squared minus 9 is the difference of two squares, and that's these two factors that we'll use as our least common denominator. The other two factors are showing up in the other two fractions. Multiplying the entire left side by those two binomials, we have 2 for the first product, and then for the second one we have the x minus 3 canceling this x minus 3, which is going to leave a positive 5 times the x plus 3 term. And on the right-hand side, the x plus 3's are removed, which leaves us with a 3 and then the x minus 3 factor. Distributing through, we have 5x plus 15, and then on the right, 3x minus 9. So 5x plus 17 is equal to 3x minus 9. And collecting like terms, 2x on the left is equal to negative 26 on the right, so x is negative 13. And again, I'm going to leave the checking to you, but from our original problem, our domain restrictions were negative 3 and positive 3, so we should be good with that solution as a valid solution. Let's look at a word problem before we get into the inequalities. If a boat travels 246 miles downstream in the same time that it takes to travel 180 miles upstream, the speed of the current in the stream is 5.5 miles per hour. We want to find the speed of the boat in still water. So filling out the table, we're going the distance upstream was 180 miles. The distance downstream was 246 miles. They're going at the same amount of time, so time is equal. And recall, distance is rate times time. So if time is equal, then distance divided by rate would be the equation for time. And the rate downstream, so the current in the stream is 5.5. So if we're going downstream, that's the rate of the boat plus the 5.5 that's helping us. But when we go upstream, we've got the rate of the boat and the current is working against us in that case. So putting all of this together, if distance equals the rate times the time, and distance equals the rate times the time. Can't see my decimal there. Let's see. Put our decimal in there. And we want to do this. Since the times are the same, we can set them equal to each other. So 180 divided by r minus 5.5 would be equal to 246 divided by r plus 5.5. Then cross multiplying, or multiplying by our common denominator, 180 r plus 5.5 would be equal to 246 times r minus 5.5. So we have 180r, and 5.5 plus 180 is 990. 246r, and 246 times negative 5.5 is minus 1353. So collecting like terms, 66r equals 2,343. So dividing by 66, the rate of the boat in the still water is going to be 35.5 miles per hour. Next, let's look at solving inequalities. When we solve an inequality, we want to state any excluded values that make the denominator 0. We want to solve the related equation, and then we're going to create a number line using the domain restrictions and the solutions of the equation, and then we're going to test some values in each interval to decide where the intervals are true and where they are false. So let's get into that. First, we see that in this particular problem, we're not allowed to have -1, and we're not allowed to have +1. So those are going to be restrictions on our number line. We'll keep these in mind. And we need to multiply through by x plus 1 times x minus 1. So setting that up, x plus 1 times x minus 1 multiplied by the left side, and then the same thing multiplied by the right side. X plus 1 times x minus 1, and we see the x minus 1s are going to cancel. In this left side, the x plus 1s will cancel on our first approach, so that's x minus 1 quantity squared on the left. And then for the next one, we have the -1 cancels, which is going to leave the +1 term, so we have +1 times x plus 1, and that's going to be greater than x minus 4 times x plus 1. So we did the first thing, stated the restrictions. Now we're solving the related equation, and we need to distribute. So we're going to end up with x squared minus 2x plus 1 plus x plus 1, and the right side will be x squared minus 3x minus 4. So putting all this together, the x squareds would eliminate from both sides. We have -2x plus 1, so we have -1x, and we're going to add a 3x, put that on the left side, we get 2x, and we've got 2 here, and we've got -4 here, so -4 minus 2 is -6, and x has to be greater than -3. So we need these two restrictions and this -3 to set up a number line. Now, we're dividing up the number line, -3, -1, and +1. And we're going to test values to find which areas are true. So the first one I tested was -4. And if we go back to the original problem and substitute into here, I believe we got 22. I got 22 over 15 is greater than 8 over 5, and that turned out to be false. So that area is not a solution. Moving to the next section, I tested -2, and my solution, when I put a -2 in each place for x, I ended up with 8/3 is greater than 2, and that turned out to be a true statement. So that section on our table, or on our number line, this is a true area. Going to the next interval, my test number was 0, and after substituting, I got -2 was greater than 4, So that area is also false. I'm going to cross that out. And finally, my last piece, I tested positive 2 and ended up with 4/3 is greater than 2, and that's a true area. This skill is something that's really valuable when you get to calculus if you are heading toward that class. So our final result is that x could be greater than 1, because we took everything here. This was all good, true in here. Or we had the true part in between -3 and -1. So -3 is less than x is less than -1. And we didn't have to test any of our points because of our inequality was simply a greater than statement. In our last example, we're going to look at a calculator example. The first one, I've already got them sketched on the calculator for you, but you can see if I wanted to solve algebraically, I would just multiply the right side by my denominator to clear that fraction. So we would have x plus 2 is 5 minus 10x, and collecting like terms, 11x is equal to 3. So x is 3/11. That's our exact answer. And a decimal value is what we're going to find on the calculator image is 0.27, or a little more than a quarter. And our domain restriction would have been x cannot be 1/2 because we can't allow the denominator to be 0. And all of that's going to show up on our image over here if we go in and inspect this. So I graphed the function. You can see x plus 2 and divided by 1 minus 2x. That's our blue graph here. And you can see this restriction at 1/2. We would not have any values at x equal 1/2. That's a vertical asymptote. You can see that there on the graph. But the intersection point, you notice what I did. I graphed the left-hand equation. That's the blue graph. And then the right equation was y equals 5. And I used the intersection point. So the blue graph is the left part is equal to 5, only at 0.27 repeating. And we did that algebraically here. Next, what we want to do on example B is we want to get the calculator and graph in our calculator window. Y1 is going to be the left-hand side of the equation. And then the second function, y2, is going to be 1/5. And then our job will be to use the intersection tool and use the intersection feature to find where the two graphs intersect. So you can tell that at plus 2, we're going to have -2 is going to be a vertical asymptote. And our graph is going to come over here in quadrant 2. And then it will be over here in quadrant 4 and 1. And then y equals 1/5 is going to be a little dotted line right in here. And then using the intersection feature, they should intersect at 4 1/4 and 1/5, which is 2/10. So we intersected at 4.25 and 0.2. That's right there. And to end the lesson, the very last piece is going to be an inequality. So we want to look at y1 is -2 divided by x minus 3. That's going to give us a vertical asymptote at +3. with a branch down here and then another branch above up here. Then y2, our y2 graph is going to be the right-hand side of the equation, x divided by x plus 4. So that's telling us we've got a vertical asymptote at -4. We're going to have a branch up here. And I'm doing this one in red. So this is our red graph. And then we have another branch that comes across here, sort of through the origin and a little bit over. Now, what I like to do is I like to grab a highlighter and then think about the question being asked, since this is our blue graph. So I'm basically looking for where is the blue graph above, because that's greater than the red graph. Where is the blue graph above the red graph? And with a highlighter, you can tell the blue graph, see the blue graph here, is above the red graph here. So we can shade that region, and it's very easy to answer the question then. So where is the blue graph above the red graph? And it happens in all of this shaded region. The blue y values are greater than all the red y values. And to answer the question using interval notation, we can say y1 is greater than y2 on the interval from -4 to +3, because we knew that -4 was a vertical asymptote and +3. And in the other two sections, the graph is above. The red graph is above the blue graph in the other two sections. Out in this area here, red is above blue, and here red is above the blue. That's the end of Lesson 6. We have one more to go in this unit.